Welcome to another edition of Map for No Reason. In this edition, we will be proving this result which connects set theory with functions. So let S be a set and A and B are subsets of S. We are looking at this function indicator A, which is defined on the set S and takes values 0 and 1. It takes the value 1 if S belongs to A and 0 if S does not belong to A. Similarly, we define the indicator of the set B. So the indicator of the set B at the point S is 1 if S belongs to B and is equal to 0 if S does not belong to B. We would prove these two results. So we begin by proving the first one, that the indicator of A intersection B is indicator of A times indicator of B. So to prove this result, we will have to prove that this result is true for every element S in the set S. Now we simplify this by considering two cases. In the first case, we consider S belongs to A intersection B. Now, since S belongs to intersection B, we know that means that S belongs to A and S belongs to B. Now, since S belongs to A intersection B, the indicator function of A intersection BS is equal to 1. Since S belongs to A, indicator function of A at the point S is 1 and indicator function of B at the point S is 1. So therefore, we see that indicator of A intersection BS is indicator of AS into indicator of BS. Now let's come to the case 2. In case 2, S does not belong to A intersection B. So any element in capital S will either belong to A intersection B or will not belong to A intersection. So this is the case where S does not belong to A intersection. Since S does not belong to A intersection B, either S does not belong to A or S does not belong to B. Now indicator function of A intersection B at the point S is now 0 because S does not belong to A intersection B. So either the indicator function of A at the point S is equal to 0 or the indicator function of B at the point S is equal to 0. So at least one of them is 0. So again we have I of A intersection BS is equal to IAS into IBS. So we see that for every point small s in capital S, we have the relation holding, and therefore we can say that I of A intersection B is IA into IB. So this proves the first part. We will now prove the second part. So we will have to prove as before, for every S in S, I of A union B S is equal to IAS plus IBS minus IAS into IBS. So again we will break it up into two cases. So suppose S belongs to A union B. Now when S belongs to A union B, we have to consider three subcases. In the subcase 1, we have S belongs to A and S does not belong to B. In subcase 2, we have S does not belong to A and S belongs to B. And in subcase 3, S belongs to A as well as S belongs to B. Let us see the right hand side in this case. So we are making a small table like thing. So S belongs to A and S does not belong to B. So IAS is 1, IBS is 0 and IAS into IBS is again 0. So we get 1, which is the same as I of A union BS. In the second case, IS does not belong to A, so IAS is 0. S belongs to B, so IBS is 1. And IAS into IBS is again 0, so we again get 1 and matches with I of A union BS. And in the third case, we have IAS is 1, IBS is also 1, and IAS into IBS is also 1. So 1 plus 1 minus 1, you get 1, and again that matches with I of A union B S. So the case S belongs to A union B is done. So let's look at the case when S does not belong to A union B. Since S does not belong to A union B, so I of A union B S is equal to 0. And S does not belong to A union B means that S does not belong to A and S does not belong to B. Otherwise, if S belongs to one of these two, then S belongs to A union B. So therefore, IAS is 0 as well as IBS is 0. So putting in the right hand side, we get 0 plus 0 minus 0, which is. So again, we see that for every S which is not in A union B, I of A union B is IA plus IB minus IA into IB. So we have proved the claim that I of A union B is IA plus IB minus IA into IB. We can easily rewrite this by using the function 1, which takes the value 1 for every point in S. So we can write this as 1 minus indicator of A into 1 minus indicator of B, and this function 1 of S is equal to 1 for all S in S. So this is the function which is identically equal to 1, and this gives us our result. This is a good point to stop. Thank you.